Welcome, everybody. My name is Anthony Price, the current chair of the Regional Advisory Committee for Europe for the SEG. I'd like to welcome you all to today's webinar, where Ashley will be telling us about how GPT, I always get that wrong, is impacting image analysis in the geosciences. Just a quick reminder on the housekeeping rules for these webinars. If you have a question, please use the Q&R button for your questions at the top. And we will endeavour to moderate those questions and get everybody answering, and also offer the choice to ask your questions verbally through the Teams app. And with that, without further ado, I will hand over to Ashley for today's presentation. Thank you, Ashley.
Yep, thanks, Anthony. So good morning, good evening, wherever you are. This slide is a little bit cut off for some reason, but the presentation today is about, it's not just about text, and we're going to talk about how GPT is impacting image analysis. I hope to give you today some insight into the world of data science, especially in relation to how we work with image type of data. I'm going to introduce myself in a moment, but I want to first frame what we're going to cover today. Now, the world of data science moves extremely fast. And I'm pretty sure nearly every data scientist worldwide was blindsided a few years ago by ChatGPT. It's been a couple years now since that first public release, but it is no doubt that it has turned some major ingrained concepts of data science on its head. So I want to talk about some of those things today. We're not going to talk too much about artificial intelligence chatbots, which is probably things that most of you are familiar with. But we're going to talk about how the same algorithms powering those chatbots are impacting our ability to use AI for image analysis tasks. So we're going to begin the presentation with some fundamental concepts and a little bit of history. And we're going to work our way up through time, up to the cutting edge where we are today, and also a little bit more into like the experimental and research grounds. I hope to leave you with some curiosity, maybe a little bit of inspiration. And for any of you working in research, possibly give you some hints where there are some places for some really interesting studies to be done. So sit back, relax. This is meant to be a talk for everybody. That means I'll be quite simplistic, but I'll provide some references if you do want to learn more. We're also going to have hopefully a little bit of fun today with some interactive videos and demos. So briefly about myself. Today, I work leading our data science delivery team in the subsurface area in Equinor. I've had various roles in leadership, project management, and in data, and today live in Norway, evidenced by the photo that if you live in Norway, you must learn to cross-country ski. So that was a pretty big thing for me moving here from the US. But my background is actually in geology. I worked for a little bit at SLB, where I developed a love for software. And before that, completed my education in geology from Wisconsin and North Dakota. So a bit about myself, and just to say that, I'm not a professional data scientist. I'm not a professional software developer. So I really am approaching today's presentation from the end use of how we use some of these types of artificial intelligence tools. Okay. First, we're going to start with one really key ground rule. When we're talking about most types of artificial intelligence that are discussed generally today, whether it's machine learning or an AI chatbot like ChatGPT, these algorithms are statistical, and they're based on a set of data which we call their training data set. For those of you with knowledge on statistical principles, it's essentially the concept of training the model on a sample of data with the hope that you can predict elements from the population. So this is a really important rule to remember, because what it means is that these AI systems cannot predict what they have not seen. Obviously, coming to the fact that if you haven't seen it in your training sample, you will not be able to see it in your prediction. Secondly, with again an obvious basics in statistics, the more input data an AI system has, the better it performs. This is a pretty significant theme for what we're going to talk about today about how we use computers to help us analyze photographs and images. Last but not least, these statistical models are probabilistic. You will never get the exact same prediction twice. You are essentially sampling from a distribution. And if you don't believe me on this one, you can try putting the same prompt into ChatGPT twice. You will not get the exact same letters or the exact same words. And the only time that sometimes this rule is violated is if there is some type of post-processing that an AI system has after the prediction to ensure that this doesn't happen. But these are some of the fundamental principles to think about today. And we're going to come back to these quite often, and especially about how the input data has really expanded to make more and more powerful models. Okay, a lot of the AI is not just statistics-based that we use today, but also has a lot of calculus and a lot of linear algebra. So there's one really important thing we need to do to be able to work with image types of data. AI is based on math. Math needs numbers. Computers only can process numbers. So how do we turn an image into numbers that a computer can work with to integrate into some type of AI? So let's look at how this works very, very simply. I have a picture up here. I'm not going to say what the picture is of, but to say that this photo is represented by a series of pixels. And the series of pixels is organized into a 12 by 16 pixel matrix, 12 along the X and 16 pixels along the Y. So we have a matrix here, but we need some information within each of those pixels, some type of number. So what we do is we can assign a color value to each of those pixels, so that each item in the matrix is represented by some type of number. For simplicity, we're using a grayscale system here, where black is represented as the number 0 and white is represented as the number 255. So we can assign each of those pixels a represented number of their grayscale color. Now, if you have a color photograph, right, then this expands into multiple matrices for the hues of blue, green, red. So then what we end up with is what the computer sees. It's basically a matrix of numbers. And those numbers give us important information about the photograph itself, but also these numbers tell us something about the relationships between one pixel to another. So now that we understand how a computer goes from an image to numbers, which we can mathematically use then for AI, let's cover a couple more foundational elements about what are the kind of tasks that we want to do this for. So I'm going to cover three main categories of why we have computers help us process images. The first one is one you're probably very familiar with. This is a category of image task called detection. And I'm showing you a photo. This is actually from Audi, which is the ability to detect lanes or detect edges. Some of these detection tasks we don't need AI for specifically. Some of them we can use some relatively simple calculus, but they are extremely helpful. And if there's any geophysicists in the room, you've probably used edge detection methods before for seismic data to help you highlight faults. In addition, we also have some other AI algorithms here that can help us for things like depth detection, which obviously also for driving systems, for vehicle systems, is also very helpful and important. So moving on from detection, we come into another large category called segmentation. Segmentation is a task where we want to look at an image and understand what things there are in that image. What segments are there in a way? And segmentation is different than detection because it doesn't just detect an object, but provides what we call a mask. And that's what you're looking at in this picture here. It provides us objects with a certain size and shape. And some of the main uses that are used pretty much every day, for example, this is from a traffic camera, security cameras. It's also common in medical imaging, for example, identifying tumors. We also use segmentation methods, for example, if you're doing AI-based horizon interpretation. But in segmentation, there's one really important key element, and that is it's up to us as humans, if I just go back, to determine what the objects in this mask are. So in this case, it's very easy for me as a human to look at this picture and say, oh, the yellow things are cars, the blue things are road. So often what we do is combine segmentation with that type of human-created label. And that then turns into what we call classification. And this is the big one, and this is where we're going to spend most of our time today. This is where you take a photo, you don't know what it is, and you're trying to predict a caption for it, what we call a label. So in this case, what I'm showing you here is a picture of a mole. This is medical imaging. And the objective of this is to have the computer determine, is this cancerous or not cancerous? So this is more advanced than just detection or segmentation. It's where we're actually giving a name to a photo and then using those names to help us predict future situations when we just have a photo and we want to get that name. A similar concept if for you have iPhones, right? You can search through your photo library saying, I want to search for pictures of my dog, right? And it will pull up pictures of your dog. So the important thing here is when we get into classification, you actually need two elements of data. You need the photo, but you also need the label. You need the text information that goes with that photo. Now, throughout this talk, I'm going to be using various, especially some seismic examples. So I'm going to put one up on the screen now. And I'm going to use examples from publications where seismic images are treated as pixels, right? Not as traces. And remember that when we're working with sort of these types of AI image analysis systems, we need to have pixels because those we can translate then into numbers. And I understand that this can be a significant assumption, right? The geophysicists out there will say, yeah, but these aren't pixels, these are traces, right? But there is a quite large body of literature and discussion that in data science applications, so in artificial intelligence applications, representing seismic as pixels is good enough. So for the purpose of the talk today, we are going to treat seismic data, traces like pixels, because it allows us to tap into this world of external technology. But I'm sure there are good arguments for not doing this as well. And so the case I'm showing on the screen now is exactly what I'm saying, where we're using a classification AI model to just say, look at a seismic cube. What is the gas chimney here? What is not a gas chimney here? Now, these types of categories, these types of tasks, fall into a concept that we in data science call computer vision. So if you've ever heard that term, this is what we're referring to. Okay, so we're going to take a step back in history now. We're going to go back to the 1950s, and we're going to see how we got from there to like these types of real cases, which are used today. Now, computer vision and AI techniques for images are inspired by real neuroscience. Also, for fun, you can keep track of how many photos of cats there are in this presentation. This is the first one. But essentially what happened is in 1950s, there were two Swedish scientists, Hubel and Weissel. They discovered that brain activity in a cat reacted to lines and edges when shown on a computer screen. And that, and that actually really started off this field into AI, into computer vision, starting with what I've already discussed, edge detection as one of these main first things that we discovered in how both the human brain and the cat brain, but also how we can program computers to sort of think like that. And of course, edge detection still exists today and has been a large element in image analysis for many years. Then it's no surprise. In the 1990s, we had a lot more powerful computing machines, and really some of the first methods of classification was face detection, right? And it's probably no surprise, this was sponsored by the US government to be able to do better facial recognition of people. This was the Ferret program, if you want to give that a Google. Now, up until about the 90s and into the early 2000s, a lot of the sort of research work into the field of computer vision was very much focused around algorithms and algorithm development. The problem was there wasn't a lot of data to really train these algorithms on. So we were kind of just making little incremental improvements. In 2009, something serious happened. And I'm going to let you hold that thought for a minute because we're going to talk about one really important problem that was happening at this time. It's still a problem today. So coming back to our picture, I'm not going to say what this is, but for classification, for an AI system to be able to identify what is in an image, we need to train it on something. And to train classification, we need both the picture, of course, which we can now convert into numbers, but we also need something else. We need the label. But finding out what a label is and determining what labels are and being consistent about it is not a trivial task. So if I look at this picture here on the far left, I could maybe interpret it. Could this be a light bulb? Maybe someone else other than me sees a face. If it is a face, do you call that a face or do you call it a person? Do you be more specific? Are you more specific by saying it's a bearded man? Is it Abe Lincoln, the 12th president of the United States? And is it better to just say, oh, this is a US president? So I hope you understand a bit of the problem here, that actually picking the right labels for photographs in order to train an AI to identify them later is not always a trivial task. However, classical computer vision needs training on a set of photo and label pairs. In addition, if you remember our fundamentals we talked about in the very beginning, the more input data you have, so the more photo and label pairs you can train the AI on, the better it's going to perform for new photos that it needs to identify the label. So just to drill the point home, if I want to ask my Abraham Lincoln AI model, hey, here's an old photo of Abe Lincoln. Is this him, yes or no? Please predict for me whether this is Abe Lincoln or not. To make that model, I need to train it on a whole bunch of different sets of photographs of Abe Lincoln with the label consistently labeled as Abe Lincoln. And of course, I have to account for different ways he might be facing the camera, different pixel resolution. Again, it's not a very trivial task to assemble all that training data together. And that was the big breakthrough in 2009. And is one of the most cited papers in all of data science. Some of you might know this. It's ImageNet. Essentially, what happened is that you were able to have the crowdsourcing of 3.2 million image and label pairs on, I would say it's a set of data representing most of human knowledge in a way. I'm just showing a picture here on the slide of geological formations. And, I really recommend reading this article, The Data That Changed the World. It's fantastic, but gives the point that if you only had 5 photos of cats, you only have 5 camera angles, 5 lighting conditions, maybe 5 types of cat. But if you've seen 500 pictures of cats as an AI model, there's much higher likelihood that you can predict other pictures of cats. And it comes back to some of the things I learned in school, right? The best geologists are those who have seen the most rocks. Well, this applies the same way. The best models have seen the most data. And from here, things exploded. So ImageNet was a huge breakthrough because finally you had this massive set of image and label pairs that you could build extremely accurate models with. So ImageNet allowed for development in algorithms that could really learn the statistical relationships between pixel information, so image data, and their labels in a very high dimensional space. The first one really to sort this out was AlexNet. And that really opened up the concepts of deep learning convolutional neural networks for image analysis. And what I'm showing you here in this video is a 3D representation of this high dimensional space that these models are able to learn and sort out. We call this embedding space or latent space, and we can measure likeness, for example, between 2 photos of cats using vector math, where the likeness between 2 photos of cats would be very high compared to a picture of a cat and a picture of a banana, for example. If you want to play around with embedding space, you can give it a go at projector.tensorflow.org, which is where I've taken this video from. We're going to come back to a little bit of this later. Now, I mentioned that with ImageNet, you're talking about pretty common photographs. So you have pictures of, outcrops in this case, pictures of cats, pictures of dogs, pictures of food, very general purpose type of image. But what this allowed us to do is because ImageNet and AlexNet and some of these algorithms being developed at this time allowed us to sort of have this sort of preset latent space of knowledge, it allows us to work off top of them. And the first real applications of this was trying to work with seismic data. So this was a huge thing in 2018. TGS put out a competition on Kaggle, and I remember this very clearly. And the idea was that could you build a model to automatically detect salt versus not salt in photographs of seismic? And the award was 100,000 USD. I mean, that's crazy, right? And over 3,000 individuals and teams participated. So all of a sudden now you say, okay, we can actually have algorithms that can sort through this much data and information. And we also have sort of these pre-trained models which allow have some starting point in being able to map this embedding space and actually understand concepts of similarity. However, you may argue today that salt versus not salt, looking back at 2018, maybe that's not the most valuable case to look at. But this kickstarted a lot of AI application into seismic data, including fault and horizon detection, segmentation and classification, and even into the commercially available tools today. I'm not even sure how many masters, PhDs were actually based on this. And this data set continues to be used today for other applications in data science. Now, we still have the problem here, though, that somebody has to go look at these pictures of seismic and say, okay, I'm going to train the model here, so I need to take a few of these and actually label them, which parts are salt and which parts are not salt. So someone still has to put in a fair amount of manual work to train the AI to cover the different, sort of population distribution expressions of how salt can look like in seismic. So about the same time, you had a different way of approaching the labeling problem. So the question was, okay, it's really time intensive for a geophysicist to spend their work hours sitting here and determining what is salt and not salt, or what is a channel and what is not a channel. So can we bypass that and, for example, start from the label instead and create synthetic data off of that label? And there's several examples of this. I remember a really great paper and presentation from Shell, this would have been Griffin in 2019, and they took this route by creating 20,000 synthetic seismic data sets from geologically realistic models where the labels were already predetermined. And then, of course, to simulate seismic data, they add some things like noise. But significant human time is still needed for that synthetic generation process. It's still not a trivial task. And so in the end, which ends up being better? Do you start with the images and add the labels, or do you start with the label and create the image from it? I'm going to come back to this point as well, because I think what we're starting to see in sort of more the cutting edge applications is that actually working with real data is better, but I think this is still something that can be looked into. Okay, before we leave our history lesson behind, we need to look at one more key topic, and something that has developed alongside of these types of applications and algorithms, and that's metrics of trust. Now, there's a few dimensions we look at as data scientists when it comes to trusting an AI system, and that's going to give you an accurate prediction. One of them is sort of the internal accuracy metrics of your specific model itself. For example, how good is its recall? How good is its accuracy? If you hold some data out, right, like how well does it predict that data? So we have these sort of internal metrics that we can use. Another one that developed about the same time is explainability. So this is the ability to, quote, open up the hood as the model is running and understand what the model is doing, especially when you're doing something like deep learning. One other is the concept of benchmarks, basically creating exams for machines, basically creating a test for AI. Now, I don't have time to go through all of these today. We're going to just look briefly at benchmarks because it's actually a really hot topic for GPT and other large language models as well. And it's also another place where I think maybe the geosciences haven't quite so well included. So I think that's why I want to talk about benchmarking specifically today. So benchmarking is commonly used to determine accuracy for an AI system based on a set of specially designed tasks from humans. It's essentially giving AI a test, a quiz. And one of the first benchmarks, and actually one we still actively use today, is called VQA, Vision Question Answering. It's a fairly simple exam that us as humans can get right pretty well. And essentially what happens here is the machine is given a question, for example, who is wearing glasses, and two contrasting images. It needs to be able to answer the question correctly for both. Now, for us as a human, this seems like a pretty trivial thing to do. We can look at this picture of who is wearing glasses. Okay, in this photo, the correct answer, it is the man. And in this photo, it is the woman. But the thing is that the reason why we use these contrasting images in VQA is that it's the same reason that if you take a multiple choice test and you choose B for all of the questions, you're going to get a pretty good percentage right just by sheer luck. So having two images actually helps us to control a bit for chance. Remember VQA. We're going to come back to this at the very end, but I definitely encourage you to read the paper if you're interested, making the V and VQA matter. And these are some of the benchmarks that we use today to just help us understand, hey, how good are these systems anyway? Okay, so we finished up with our history lesson. Now let's move a little bit more toward the cutting edge. So enter ChatGPT and a concept called foundation models. Well, we're currently finding ourselves in a race to achieve the dream, which is can a single mathematical model self-organize the entire population of human knowledge and thus be useful for any task. In other words, one AI to rule them all. And whether you want to call this AGI or whatever you want, but just to say, can we actually train a singular AI to understand every concept in human knowledge? Well, as of today, the answer is no. We're not there yet. But the concept of foundation models was born, like GPT-3 and GPT-4 for text data. These foundation models hope to cover a broad sample space. They can cover everything from cats to bananas, right? In hopes that they're useful for many tasks out of the box. But that these also can serve as a foundation for augmentation for special needs, right? So for example, if you have this big foundation model like GPT-4, it does have some concepts of geology in it, right? It knows a little bit in its embedding space where concepts of geosciences are. But you can use that as a sort of stepping stone to say, hey, I want to augment this even more for specific geoscience cases. Now, the preciousness of these foundation models, like ChatGPT, and some of them actually handle both text, image, and other types of data, like documents. And the other really fascinating thing here is that they aren't explicitly taught. If you remember our classical computer vision, right, our Abe Lincoln, we have to feed it in a series of photos of Abe Lincoln with the label Abe Lincoln. These models don't have to do this, at least not to the same degree. So they're able to do something called self-learning, which we're going to come back to in a moment. Now, I want to push in the point a bit more about how big these models are getting. They're sort of coming up to this sort of AI, one AI to rule them all concept. So to illustrate what I mean here, I'm pulling this plot from Stanford's AI Index. And we can look at this plot. On the x-axis, you're looking at publication date. On the y-axis, you're looking at number of tokens. The units are in tokens, so we can approximate this close to 1-to-1 for words. So the very top of the y-axis here is 100 trillion tokens, which would be around 90 trillion words, give or take. Gets a little tricky to measure in terms of reality, but I've seen some statements online that 100 trillion tokens is approximately all high-quality readable text on the entire internet in any language. So if we look at this plot, down in the lower left corner, you'll see AlexNet, which was the first model that was trained on ImageNet with very good success, good accuracy. And then you can see this rapid growth in how much data has gone into the training data sets of these new algorithms such as GPT-4. You can see up in the top right corner, Llama from Meta, and of course, DeepSeek as well. So we're up to about the 50 trillion token level or so. This graph isn't updated for 2025. Will we make that 100 trillion? I don't know. But just to point out that the size of these models is immense, and the amount of knowledge that they capture in their training data set is really approaching this sort of dream. Now, and as you can see, due to the sheer quantity of data here. If we're talking about image classification using this type of model, it would be impossible for a human to manually label all the images, for example, on the internet. So, like I said, these foundation models use a special method called self-supervision to be able to basically create its own training data. So let's look a little bit about how self-supervision works for image types of data. Okay, so if you're counting cats, here's your chance to count some more. Self-supervision is a relatively simple concept. I could make it very complex, but we'll keep it very easy today. It's also a similar way as to the large language models work, but we're going to stick with talking about image data. Concept is relatively straightforward. What you do is you allow images, which of course we're turning into these matrices, right? And convolutions of them. So we change them around a little bit, flip them upside down, turn the matrix inside out. We allow them to sort themselves into this high dimensional embedding space. So to illustrate this, I have in the far right corner of my 3D representation of a very high dimensional space, photo of Chapo, the cat. Now the convolutions are, for example, turning it upside down, making it grayscale, making a crop. And what I can do is I can allow this self-supervision to say, hey, here's another picture of a cat. It's yawning. It looks pretty similar to this picture of a cat. I'm going to sort this into the same space here. Now, on the other side here, in the lower left corner, we have pictures of a cappuccino. And you have a crop of it, some convolutions of this. And what we can do essentially, once we have this embedding space, quote, learned by a model, the simplest way that we as humans can come in is with a couple of labels. So for example, say, hey, this is the group of sleepy cats over here. It then knows that this whole group is representative of sleepy cats. Now, foundation models also need to be able to generalize between groups of images. So if we know that our lower corner here are cappuccinos, then this allows us to say, hey, I've got this new image. Oh, it's a sleepy cat cappuccino. And this is, for example, how AI-generated art also can work. So this allows us to have the self-supervision, which if we just do a little bit of labeling, we are able to essentially label the entire knowledge space. And I want to highlight on one geoscience application of this, there are some things happening in the world of seismic when it comes to foundation models. And definitely, I think it's probably worth another SCG webinar to find someone working on those. But I want to show you one for microfossil images. This example is called Scampi. And it's a foundation model. It's a foundation model for helping to aid in the identification of fossil images. So to highlight the point here of why these foundation models and this concept of self-supervision is so important for us, is that this model was trained on 1.65 million pictures of fossils. But the actual amount of human labeling, they only had to label 1,123 images. So if you go from sort of this classical computer vision, this classical classification we talked about in the beginning with our Abe Lincoln example, we're reducing the amount of time by using some of these new self-supervision methods. So very cool. It's actually making this type of AI way more valuable. And we're not taking, for example, a biostratigraphy expert's time in labeling 1.65 million photos, right? Okay, before we end today, there is one more key concept we need to discuss. And really something happening all over the place right now. I'd say it's still a little bit immature, but it's a really, really fascinating area. And that is concepts of multimodality. I see my video is going to play here in a minute. So the last concept here is when we're looking at image analysis is that instead of training a model to create an embedding space, which is what we're trying to represent here. So this is just a representation of a high dimensional space where we've grouped hand-drawn digits into different parts of the space. So instead of training a model to create an embedding space for just text or just for images, we can train a model to sort different types of data together and allow us to do automated tasks and predictions across different types of data. So again, like here's on the left side here, this 3D representation of latent space. And in the middle here is this big cloud of the number 4. So a bunch of photos of people who have drawn or written the number 4. In a multimodal situation, we don't only store these type of photos, but we also can store information related to it in different data formats. So for example, we could store different types of related text, the digit called 4. She was called to the front of the class and started writing 4 on the chalkboard. The subtraction of 6 from 10 is 4. You can start storing things like video, right? So now you have like, here's a children's video for how you draw the number 4, right? You can even add things like other photographs. So you can relate these. We talked about this already with Chapo the cat. You can even add in things like audio. So for example, a sound clip of someone saying the number 4. So that is the concept of multimodality, is that we can form these large latent space embedding spaces with concepts more than just one type of data. We can fill them with relationships to many different types of formats. That allows us to do something pretty amazing. Now, in other words, our sort of classical computer vision has changed dramatically, where we have gone from just saying, okay, we can do an image and a label. And now we're entering a world where we can say, I can go from an image to a video, an image to audio. I can go to image if I want to. I can go from language to image. Hey, generate for me a photo of 2 cats playing poker, right? And maybe most importantly, instead of having concepts of singular labeling, we're going more into an area where it's an image and language that describes it. So entire elements of context. And I want to capture you very, very quickly what multimodality looks like. For those of you who are data scientists, you know this already, but for those of you new here, this is just to show a quick example. So I'm just opening up Microsoft Copilot, and I'm going to ask it just to describe a photo for me. So this is using a variant of GPT 4.0, which is a multimodal model. I'm going to upload a picture of Chapo, my cat, and just ask it to describe the photo for me. Remember, GPT has never been trained on a photo of Chapo, my cat, right? But yet it can correctly label this image, meaning it can go from image to language. This is multimodality in practice. And you can think about how you might use this in the geosciences. For example, here's a core photo. Can you interpret this for me? Or here's a thin section photo. Can you also look at what type of minerals might be in here? So there's some really interesting applications that I think we're just on the cusp of being able to use in the geosciences. Okay, so to sum it all together, what we have is concepts of multimodality. So we saw in this demo, GPT 4.0, which is a foundation model that allows for both text and images to live together in its embedding space, allowing us to do cool things like from text to image and from image to text. And multimodality anchors that foundational model to real data, text, images, audio, video, time series. And we have a special name for these types of AIs. We call these VLMs, or Vision Language Models. And one open source VLM that you guys can use if you're working in research is called CLIP. It's also from OpenAI, but it's a completely open source model to be able to use. And it's a foundation model where the embedding space is pre-set up for us and trained on a set of 400 million image and language sets. Let's see how it works. So we're going to do a bit of an experiment. And the experiment I'm going to run for you today is the idea that CLIP, which is pre-trained on some set of images, can it generalize to understand a geoscience image? Let's run an experiment to see if that's true. So what we're going to do is first we're going to see if CLIP can work on regular images, just to show you guys how CLIP works out of the box. Then what I've done is I've gone into some final well reports from the Australian public data set, and I've taken out a few pictures of annotated seismic sections and their captions. So I have a set of image and language pairs, essentially. Now, remember, we're doing all this into this large latent embedding space where we use vector math to describe similarity. So our hypothesis is that CLIP can distinguish differences in cosine similarity between the image and language pairs. So if the correct image and language pair have a high and distinct similarity value, that means CLIP is able to distinguish it. It's able to put it into a place in its model, right? Otherwise, CLIP doesn't have enough information to sort this type of data. So let's just begin with the real basic overview with just some very general images to give you an idea on how CLIP works. This notebook you can actually download yourself from CLIP's GitHub repo if you want to give it a try yourself. I'm going to fast forward a little bit through things because just for the sake of time, we're going to install the model. We're going to use a vision transformer. Don't worry if you don't know what that means. We're going to pre-process the images and the text information, and then we're going to pick a couple images. So I'll just stop here a minute. So the images we're picking here are just general purpose. So we have a picture of a page of text, cat, who's counting cats, astronaut, rocket, a picture of a human retina, and a silhouette of a horse. Yeah. And then each of these images has an associated language. So what we're going to do then is we're going to put these into CLIP, and we're going to calculate the cosine similarity and look at just the quick results here. So CLIP is able to sort these into its embedding space. So you see the highest cosine similarity. Similarity is most high. The text about segmentation, it finds that one correctly, 0.35 over the other images. However, there's one interesting thing, because we have these two pictures, one of an astronaut and one of a rocket. And if you look at the bottom row in this confusion matrix, an astronaut with the American flag as the text, it does pick the correct most similar one, so 0.28 for the picture of the astronaut. But you'll notice it's not too different than the picture of the rocket. And that's because CLIP is pre-trained on concepts of space in a way. So it's understanding, hey, there's actually something quite similar about these two images. Okay, so let's move on to seismic sections. So just so you know, I'm pulling these things from NEATS, the public portal for Australia data, and I've just gone into a few final well reports here. And we're going to set up CLIP again. We're running this in Google Colab with GPUs, by the way. And we're going to load in a few seismic sections. So I just want to show you briefly what these look like. So the first one we have is Bratwurst, Stolpen, and Eula. So we have 3 seismic sections here, each with a textual description. We're going to build out the features, and then we're going to do our same exercise of calculating cosine similarity. And this is what we get as a result. It can't distinguish any of it. So the cosine similarities are nearly identical between the text and the image pairs. It cannot tell the difference between these 3 seismic sections. So the answer is our hypothesis, at least in my 2-hour effort, is proven wrong. CLIP out of the box is not good enough for seismic sections and associated geoscience language. And this is the reason that we're seeing more specific foundation models being created, for example, for seismic, or as I showed previously for SCAMPy, for example, microfossils. So coming to the end, why do we do any of this? What's the point here? Well, I think that's still a bit to be determined. We're luckily an industry very rich in language image type of data. I mean, think how much thin sections, cutting images, seismic sections we've already described and put text with in reports, PowerPoints, research papers, professional collections that could be used to adapt a model like CLIP. And there's a few tasks that we could use these new types of interactive type of GPT systems with. First one, classification. Automating tasks like core descriptions or aiding as an additional interpreter looking at maps or seismic sections. The other one that's really interesting is more semantic search tasks. Can we use this type of capability to help us search for experiences, knowledge, and analogs, either via language or via photo? So for example, could you find similar thin section photos to the one that I have here? And I will say that there's been little research or application on these types of questions so far. There have been some nice papers this year. Asiv and et al. 2025 had one in Leading Edge back in February, and refer you to that paper if you want to know a little bit more about these types of cases that we're interested in. So what's happened to our benchmarks? How have AI systems like GPT or CLIP done on our VQA test? And I'll just summarize this saying VQA, remember who is wearing glasses, the man or the woman, it's not hard enough anymore. GPT 4.0, which is this pink, graph here, is just showing that VQA in the pink line. The AI systems today now do better than a human does on that exam. What does that mean for us in the geosciences? Well, how do we make benchmarks more specific to our domain, which is something, in my knowledge at least, we haven't done yet for geological images? And simultaneously, how do you make the style of benchmarks more difficult? And often this can be done by including concepts of reasoning. That leads us into an interesting situation because often geoscience images have secondary meaning and interpretation, and ground truth is often left untested and unknown. So how do you make a benchmark for geoscience images that captures that uncertainty? And this is a classic example from Heron in 2015. Find the unconformity on the seismic, and of course, you have a ton of different interpretations. So to conclude, key takeaways, there is no doubt that we take more images in the geosciences included than ever before. So how do we work alongside computers to process all this information in a way that is fast and accurate enough for the job at hand? Probably most of us aren't doing this. We're not using these AIs too much today. I would probably ask the question, why? And maybe these vision language models will help us with this. Secondly, GPT technologies, multimodal foundation models, they have a lot of potential for us because we are an industry rich in visual and language media. And we're able to remove some of these labeling tedious work challenges of the past. But it requires us some more advanced trust exercises, creating benchmarks. It brings up the question as to what is real in subsurface, but there's fantastic opportunities for research here. And lastly, will we start seeing more subsurface data treated like pixel-based images in the way that we do seismic today? Will we see this for time series plots, schematics, and will we see multimodality expanding to 3D geological models? Some things to keep an eye on. So lastly, the application of AI in general is only useful if there's a challenge worth for people solving at their desks. So this is something that we as a community have to want as well. But what I do know is that the data science and artificial intelligence train is moving fast. Blink and we will find ourselves behind. There's a real golden opportunity right now for us to hop on. Thank you. Open for any questions.
Thank you very much, Ashley, for a really interesting presentation. There's quite some good, challenging questions there. So with that, I'll take you over to some of the questions we have in the Q&A, and I'd encourage the audience members, if they have any questions, to not hesitate to put them in there. We still have some time to cover some of these questions. So the first one is from Per, asking if you have experience using the UNet supervised learning architecture deep learning model for seismic image analysis tasks, and furthermore, what are the pros and cons of applying for this kind of image analysis, and is it trustworthy?
Okay, I probably don't actually have a good slide for this. Do I have experience applying UNet? Not practically in my own work. I don't do a ton of data science these days, but we have some great experts, especially at Equinor and throughout the community, who are good with UNet, especially in application to seismic. I think one of the big questions that we have today when we're looking at an image classification task is, are you going to use a convolutional neural network, like UNet, for example, or are you going to use a vision transformer? We often have a choice in actually what type of model algorithm family we want to use today. And I think we're still uncertain which is best. So the practice at the moment is actually to test on both and see which one gives you a better result. So I think that's where I'll put that today. Can you just repeat the second half? I think it was something on accuracy.
Yes, of course. So it was asking about UNet experience. What are the pros and cons of applying for seismic analysis? And do you think it would be trustworthy?
Yeah, so I have, And I think this is something that I didn't have time to fit into the presentation today, but one of the nice things with UNet and sort of these convolutional neural networks, especially for seismic analysis and other image types of tasks, is that we have a lot of great explainability methodologies. So with convolutional neural networks, we can actually open up the box and look at each of the layers and understand what the algorithm is looking at the point in time. So for example, seismic, if we're interested in classifying or doing something to say, hey, this is a Cretaceous reservoir or this is a gas chimney, right? We can actually pull that open with some of these explainability capabilities and say, yeah, it's actually looking at the gas chimney. So I think that's maybe one comment, is that in terms of vision transformers, we maybe don't have the same explainability capabilities that we have today with CNNs.
Excellent. Thank you, Ashley. And I'd like to add a bit of commentary to that, if I may, as well. I can't speak directly from experience, but I do have some colleagues that have been using UNet-type machine learning for some of the geoscience applications and sticking some physics in there too. And I like your comment about being able to open the box and have a look at the layers and see which bit it's reacting to. Because, yeah, it's a good framework, as far as I understand, to put in some physics to do some of those synthetic forward modelings to help train the system. Okay, moving on, if I may. There's also a question here in the chat about going back to earlier in your presentation where you were talking about counting cats. And it's kind of a classification question, I guess, asking with the cats, do they count as separate cats, or if not, are they just an augmentation of the same cat? So this is where I think it's getting into the categorization idea.
I think Dave is making a multi-level joke with this comment or with this question.
Okay.
But
yeah.
If I go back to this slide, this is something that we do both with neural network architectures and also with self-supervision, where we want to be able to convolute an image, right? Because we are trying to get at that original problem that we have, that ImageNet was trying to deal with, right? Where the fact that we have to try to simulate, in a way, a population of different scenarios. And you don't want to manually go out and collect all of those images, right? So all of the different ways that someone might take a picture of a cat, for example. So I think that's just the point, is I don't have numbers of what it could be. Maybe a hint. I just looked this up yesterday. It's not for sure because it's just some chats from Reddit. But for example, in GPT 4.0, which is a multimodal foundation model, I think they have somewhere between like 3,000 and 16,000 dimensions that they're mapping in their embedding space. So my guess is there's probably a lot of pictures of cats in there.
A lot of pictures of everything, I guess.
A lot of pictures of everything.
Yeah, the training data sets are really getting very large, as you've talked about at the beginning. Yeah. We have a question here from Paul A. Gillespie asking, starting with a statement of, you indicated that manual training is often best for training a CNN, but is this realistic for 3D data such as seismic, for which synthetic models may be better?
This one, I wish I had a more concrete answer for you. I think this is probably still an area where we don't have one clear answer or winner over another. I think it comes back to a little bit of the point that we are dealing with a situation where we don't have hard photographs of things, like in the same way where I can take this picture of my cat sitting on a couch, right? We are dealing with, at least in the case of seismic, we're dealing with secondary imaging in a way, right? So I think the jury's still out on this one, Paul, if you're listening. Which one is better, synthetics or real data? At least what we're seeing from the sort of VLMs, these vision language models, is that they actually act better with real data. At least it's something we're seeing. And I know there were some discussions in EAG this past summer about seismic foundation models, and I think they'd also come to the same conclusion that the real data did perform better. Yeah. I think it's a great discussion point and something that, yeah, many in this room could probably discuss further. Yeah.
I guess we need to keep an eye on that space.
Yeah, definitely. Yeah.
The next question we have in the Q&A is from, I think, Akert Tolstrup. Apologies if I've mispronounced that. So saying this is really exciting. So how does a complete novice start testing these techniques on seismic and polygonal seismic cracks? I guess the Jupyter notebook example that you had up earlier might be a good place.
Give it a start. It depends a little bit what you're looking for. If you're looking at sort of fractures or cracks, then maybe edge detection is all you need, right? In that case, you don't even need AI. You just need some simple derivatives. But if you're interested in testing some of these concepts with these vision language models, give the Google Colab notebook a spin. You can download it right from Clip's GitHub repo. It's public, it's open source, and it's licensed for research use. So it's something that you can use for learning and use for testing ideas. Yeah, give it a spin and try some of your ideas. I put together this demo, I'm not kidding you, it took me about 2 hours. So I think that's an amazing thing, actually, that the accessibility to techniques, method, and code has never been easier for us, especially coming from a geoscience background, like tapping into that external technology world. It's all there on the internet. And yeah, these things are just here waiting for you to learn them. Yeah.
And I suppose you could use GPT to help you write it.
Yes, it can probably help you out a bit, but it is good to understand a little bit about how the code is actually working. Yeah.
Of course, yeah, you need that background training data set. The next question we have in the Q&A box is from Victor Adolfo Escobar Betancourt, asking, are there any open initiatives about benchmarking in geological seismic images?
I haven't heard of any in images. I think I mentioned that in the presentation today. It's definitely something that we could use some work on. I know there are some open activities right now on text information. So, for example, benchmarks on seeing if these types of GPT chatbots can answer correctly what formations were penetrated in the drilling of NO 13/4-A, right? So we have some work happening on benchmarks open, especially here in Norway, for text data. I haven't heard of anything happening on image data. So if there's anyone out there interested, I think that would be a really cool project. Yeah.
Excellent, thank you. The next question we have is from Sukjun Pyun, asking, how do you foresee the future of supervised learning based on synthetic data? Once foundational models become more mature, will training with synthetic data no longer be necessary?
I can't answer that for you, but I think you're hitting on what people are trying to understand right now. That's exactly what people are trying to do research into. Yep.
Excellent. We have another one from Victor Betancourt asking, could seismic amplitudes or attributes ever become part of the multimodal models? I would guess so.
Yeah, that's what I'm saying. We're in a really golden opportunity here for geosciences research, because we've shown that multimodal models, coming from sort of DeepSeek and Meta and from these big tech companies, they can handle things like audio, which technically is kind of like a time series and kind of like a trace, right, in a way. So I think absolutely, but I haven't at least seen any research papers. There could be some out there giving this a go. Not sure.
Yeah, that would be interesting. We have a question here from Darren Mortimer asking, what are the risks to self-supervision? How do you know the initial training set is sufficient?
Yeah, so this is why I talked about some of these elements of trust, right? Because it doesn't matter if you're using self-supervision techniques or if you're using some of the conventional manual ones, what your result is how accurate is your model at the end of the day. And this is why we look at, for example, internal metrics within the model, right? I don't know how OpenAI does this, for example, GPT. Might be interesting giving in a Google, but this is also why we're using large benchmarks, right? Because these benchmarks also need to cover this huge set of knowledge. For example, the VQA, which was released in 2017, that's 1.1 million image pairs, right? And then it's also the concepts of, for more of the neural network architectures, a concept of explainability. So opening up the box, understanding what the models are doing. And I think we'll see those explainability methods also adapt toward more of these foundation models too. So yeah, I think that's the best answer I can do on this one. Interesting question though. Yeah.
Interesting. We have a question here from Dr. Essam Aboud, I think that is, asking, what do you think AI will be in geoscience after 10 years from now?
10 years from now, I think searching is going to probably be the most significant impact we're going to see. I put some of these questions up here on this slide here. So what do we do with some of these things? And I think, honestly, if I look 10 years from now, I'll be honest, the geosciences and maybe the oil and gas industry were a bit slow in adapting new technology. I'll be honest on this. But I think the fact that we have such a rich set of literature, data, I think that the searching capability is something will be very different for us in 10 years and how we actually find data and information related to geosciences.
Excellent. We have a quick question from Fergal Murphy here asking, do you have any experience applying CLIP to other geophysical imagery? For example, something non-seismic like airborne geophysics, airborne gravity magnetics, I guess.
I have not. I've had some experience with dealing it with outcrop photos. So it is adaptable, but it does take some work, which I think is what I proved with my little hypothesis experiment. Yeah.
Need more training data, I suppose.
Yeah. And you need to have it be the right distribution of training data.
Well sampled.
Yeah.
Okay, we have a question here from Omar Marbet asking, how do you see multimodal models like CLIP or GPT-4V being applied in geoscience workflows, where data often combines images, text, and other signals such as seismic sections?
Yeah, so how I see them applied, I think I come to these classification tasks and search tasks I have on the screen right now. This is really sort of what we're trying to get at. So can you relate information from various data types together to give you a more comprehensive analysis? I think one of the places where I expect this to come is in core descriptions, core photographs, thin section photographs, SEM photographs. I think seismic is a bit trickier, to be honest. Yeah, I think, yeah, I'll keep it like this, I think.
Fair enough. We have at least one last question on the list here from Giuseppe Amendola. There might be one more actually, asking, saying thanks for the great presentation. Yes, thank you. This has been very interesting. And also asking, can you elaborate a bit more on applying the self-supervision to a CLIP model for seismic image and text pairs?
Giuseppe, talk to me later. I have a GitHub repo I can share with you.
Yeah, that maybe needs a bit of offline time.
Yeah.
And there's a question from A. Kurt Tolstrup again, asking if your CLIP slide talking about GPU runtime, does that mean that he needs access to a higher power computer? I would think yes, rather than my 10-year-old high-end laptop, or is this all running on the cloud?
Okay, so when we're talking about image analysis in general, we're usually using your graphics processing unit on your computer. So you can do things like CLIP on your own machine as long as you have a powerful enough GPU. Otherwise, you might be waiting some time. But what I showed you is a tool called Google Colab. And this is essentially, you can think of it as a virtual machine. So it's running on Google Cloud, and you can pick from different computation needs that you might have. Some of them you have to pay for, some of them are free. In this case, I've then picked to do the processing on GPU, graphics processing unit, because we're dealing with image data. Yeah, and very short.
Well, thank you very much, Ashley. I'm afraid we're just about out of time. We've had some excellent questions and discussion, and following a very, very interesting presentation. So I'm sure everybody here in the audience would join me in thanking you warmly for your presentation today, and looking forward to seeing how this subject evolves.
Yep, thank you all.
Thank you. So on behalf of the SCG Europe, I'll close this webinar and look forward to seeing some of you at the next one.
Bye-bye. Have a great day.
You too.